Now, the topic of mathematical induction is found to be very difficult by a lot of students. And I think why that is, it's not really something that we apply in everyday life, and it doesn't really apply to that. But it's more of a pure mathematical process. So I think a lot of students have trouble imagining what it means to just have a pure mathematical process. But hopefully, by the way that I've explained it in the next couple of modules, it will prove to be very easy. Alright, so let's start off by actually exploring what does mathematical induction mean? What is actually meant by all of this? Well, I want you to think about mathematical induction as a formal proving process. So it's a formal proof to show that the left-hand side equals the right-hand side. And because it's a formal proof, that means that all the steps I teach you, you'll have to follow exactly. So you can't just even have one word or one step different because it's formal and then you won't get the right answer. So consider it as a formal proof. Now you're probably all wondering, why do I have a picture of dominoes up on the board here? Well, that's because dominoes is actually an excellent analogy for what mathematical induction is. So if mathematical induction is a formal proof, then we're going to be proving that these dominoes will all fall over. Okay? So that's a proof that I want to have for the dominoes, is that they will all fall over. And I'm going to use the process of mathematical induction to prove that. So starting with step 1 in mathematical induction, we show that the statement is true for the initial value of n. So what that means for the dominoes is that for them to all fall over, there has to be an initial starting point, doesn't it? There has to be a force that starts to push them all over, right? For them to even start falling over. Another way you can think of it as is, for example, in a car, for it to start, you need that initial ignition. Without it, that ar won't ever start. Now, the other reason why dominoes is a great analogy is because the idea of mathematical induction is that once you start it, it just keeps going. So it's a self-perpetuating process that once you've pushed the first domino over, you'll keep going. So same with mathematical induction. If you show it's true for the first one and then for the whole idea, then they'll all be true. So that's step 1. Moving on to step 2, this is where we assume that the statement is true for n equals to k. What this means for our dominoes is that each of these dominoes, so for example this one over here, is making the assumption that if the domino in front of falls, it's going to hit that domino and that domino is going to fall and hit the next one. Okay? So we're making a basic assumption here, and that means a key word is assume. So whenever you write step 2, I want you to make 100% sure that you have the word assume in there, okay? We're making an assumption. That is a basis of step 2. So now we've made that assumption, we can move on to actually proving that the statement is true for n equals to k plus 1. Now what I'm proving here is not only am I assuming that if that falls, it's going to hit the next one, now I'm actually proving that if the domino in front falls, then it's going to hit me and I'm going to hit the next domino. And then it's going to keep going, okay? So this is what we're doing here. We're proving that, which means that if I've proven that, yes, there is a starting force, and I've also proven that if that falls and hits the next one, then it will hit the one after that, then I can make the conclusion that it follows the statement must be true for all values of n. So in other words, I've proven, I make the conclusion that yes, the dominoes will all fall over. What I've taught you here is step 1, step 2, and step 3. Now there's technically a 4th step to mathematical induction, and that's your conclusion, okay? So whenever you think about mathematical induction, I want you to think about step 1, which is the ignition, the starting process. Step 2, when we're making an assumption that if one falls, the next will as well. And then using that assumption, in step 3, we prove that that's true. And finally, we have to make the conclusion that if there is a starting process and we've proven that the next ones will fall, therefore they will all fall over, or therefore it must be true for all values of n. Okay, so remember, mathematical induction is a formal proof for left-hand side equals to right-hand side. So now let's look at an actual question now, because I'm sure you're getting a little bit antsy about what this actually is going to look like. So in question 1, we have this, which is proof that 2 plus 4 plus 6 plus so on till 2n equals to n times n plus 1 by the process of mathematical induction. Now, before we start, I want to make sure that we actually understand what this question is asking. What it's asking is that the left-hand side, for us to prove that the left-hand side equals to the right-hand side. That's a basis of mathematical induction. Now, the other thing I want you to understand is what that 2n here actually means. So what does it mean? 2 plus 4 plus 6, so on until 2n. What does that 2n stand for? Well, what that 2n is a general formula for each of these values. You can see that if we sub in n equals to 1, that gives us our first number, doesn't it? And when we sub in n equals to 2, that gives us our second number. And 3 gives us our third number. So this just gives us all the numbers, and the last n will give us the last term. And that's why it's so on till 2n. Now remember, to start off with proving, what do we need? We always need that first push, or the ignition process, which is step 1. And in step 1, we show that it's true for the initial value of n. So it's the initial value of n. Now we have to work out, what is that initial value going to be? And how do we do that? Well, I'll teach you that now. So what we consider is, firstly, your general formula here, which is 2n, and then we consider our first value. And then we think, what does n have to be for the general formula to equal to the first value? And you can see that n has to be 1, doesn't it? For 2n to equal to 2, n must equal to 1. So that's the first value of n that we have to prove. So why I'm saying this is because I want you to know that n can be 0 or 1 or 2 or any number. Now, 90% of the questions that we go through is going to use n equals to 1 in the first step. So it's really easy for students just to assume that it's always going to be n equals to 1. So I don't want you to make that mistake. I want you to remember that step 1 is to show it's true for the initial value of n. And then we need to always work out what that n value is, okay? All right, so how do we show it's true for n equals to 1? Well, for all proofs, we start off with the left-hand side. So using the general formula, we have 2 times n equals to 1. So 2 times 1 equals to 2. And then we look at the right-hand side, which is n times n plus 1. So that's going to be 1 times 1 plus 1, which also equals to 2. So now we've shown that the left-hand side equals to right-hand side. So therefore, we can make the conclusion that it is true for n equals to 1. So what we've done is that we've proven that yes, there is definitely that initial push, the initial starting process. Now we can move on to step 2, which is making the assumption. So assume that it is true for n equals to k. So remember, in terms of dominoes, that was when one of the dominoes makes the assumption that yes, if the domino in front of me falls, and then I will fall as well and hit the next domino. So we're making assumption here. And how do we do that once we've written that? Well, we just substitute k into wherever there's n. So this becomes 2k, and this becomes k times k plus 1. Now, I want you to remember this assumption because we always use the assumption from step 2 in our next step. So if by any chance you've somehow worked out step 3 without using the assumption, you know something's gone wrong. So I want to make sure that you're always using the assumption from here for the next step. Now, Step 3 is when we get to finally showing and proving. So we want to show it is true for n equals to k plus 1. That is 2 plus 4 plus 6 plus 2k plus 2k plus 1 equals to this. Okay? So to show it's true for n equals to k plus 1, we want to prove that this side equals to the right-hand side. So we need to write that is and then write this out. Now, how do I get this equation over here? Well, we're substituting k plus 1 to wherever there's n. So here, instead of 2n, I'm writing 2k plus 1. So how do I know that's 2k? Well, if you think about it, each of these is just increasing by 1. So if it's k plus 1, the number in front is going to be 1 less in terms of n, isn't it? So that's going to be k plus 1 minus 1, so that's why it's 2k. And the number in front will be 2k minus 1, won't it? And how do I get the right-hand side? Well, I'm just substituting k plus 1 into this equation here. So instead of n, I've written k plus 1. And instead of n plus 1, I have k plus 1 and then plus 1 again for this over here. And then summarizing that, we get k plus 1, k plus 2. Yeah? So we want to prove that this equals to that. That's what we're doing. So how do we prove? We always do left-hand side equals to right-hand side. So starting off here, we have the left-hand side equals to this portion. Now, this is where I want you to use the assumption from step 2. Can you see how we can somehow use the assumption? Well, looking at what's assumed in step 2, 2 plus 4 plus 6, 2k, equals to k times k plus 1. Can you see how this part of the assumption looks exactly the same as this part of the proof we're trying to make? Yeah? This is exactly the same as that, right? Which means that instead of writing that, I can just substitute this into here. Okay? So instead of writing that, I've just substituted k times k plus 1 instead of that. And this just stays the same. So now I'm just rewriting the left-hand side to prove it equals the right-hand side. And you can see that once we've used the assumption, we now have that k plus 1 and k plus 1 is a common factor. So I can factorize that out the front, and that leaves me with k plus 2. And that looks exactly the same as the right-hand side. So we can say that now we've made the proof. We've made the proof that the left-hand side equals to right-hand side. So therefore, we've proved this over here. So therefore, since we've made the proof that this equation does equal to that, we can say it is true for n equals to k plus 1. Now, I want you to consider what have we actually done in all these steps? Well, in step 1, we proved that it's true for n equals to 1, didn't we? And now we've proved that n is true for n equals to k plus 1. That is any number plus 1. So we've actually proved that n is true for n equals to 1. And when k equals to 1, n is true for 2. And also true for n equals to 3 and 4 and so on. So therefore, we can make the conclusion that the statement is true for n equals to 1 as well as any number greater than that, haven't we? So we can just simplify that to n is greater or equals to 1. So remember, once we've gone through the steps, we have to write the concluding sentence, which says that yes, we've actually proved that the left-hand side equals to right-hand side for all n is greater or equals to 1.